Hello, and welcome to this video about the construction of integers. In this video, we'll learn how the integers are constructed from the natural numbers. We'll also show that the integers are ordered and form a set known as a ring. These are the natural numbers, all of the positive numbers, and this is the set n0, which includes 0 as well. Integers are the set of all positive and negative numbers, and 0. An integer is defined to be an ordered pair of numbers, both of which are natural numbers. And integers have this property, that they represent the difference of these two numbers, the first minus the second. And if the first number is less than the second, then we can have a negative number, that is less than 0. Which we can't have with the natural numbers. We have to define this relation, which says that these two ordered pairs are equal as integers if they satisfy this equation, which comes from rearranging this equation, which says that the differences between the first and second numbers has to be the same for both ordered pairs. This relation is an equivalence relation, which we'll prove shortly. We'll define addition between two integers to be this, since we have to be able to add integers in a similar way for adding natural numbers. This is where we get this definition from. If we add these two integers, then we add the integer values that they represent. Rearranging the equation gives us this. So we can rewrite this equation as the difference between two natural numbers like so. And then we can pack these two numbers, one minus the other, into this ordered pair notation. We also have to define multiplication, which is this for integers. And this is where we get this definition from. We'll start with the product of two integers in ordered pair form. Then we'll expand them out into the values that these integers represent in standard whole number form. And then we'll expand the brackets and manipulate this expression to give us this expression. Then we'll get it into the form of one positive whole number minus another, which we can pack up into ordered pair form again. So this is where we get multiplication. This relation causes two ordered pairs of numbers to be equal as integers. An equivalence class is a set containing all of the ordered pairs that are equal as integers. This set is the integer itself. So this is what this integer is. It's all of these ordered pairs of natural numbers, so that the first minus the second give the same number. In this case, it is 2 minus 3 is equal to minus 1. This is a much neater way of describing this set. The second number is always one larger than the first. We can also write the equivalence class using bar notation, which we won't use here. Now, to show that these two equivalence classes, which represent each integer, are equal, we only need to show that their representatives are equal. And we only need to show that their representatives are equivalent according to the equivalence relation that we've just defined, because then they'll both be in the same equivalence class. I'll just prove a small result that we'll be using to perform calculations much more quickly. These two ordered pairs will be equivalent, so we can always just subtract the same number from both entries in the ordered pair to get an equivalent ordered pair. We'll use the definition of this equivalence relation to get this equation, which, when after having been manipulated, this equation shows that these two ordered pairs are equivalent and represent the same integer. So now to prove that this relation is an equivalence relation, we have to show that it is reflexive, symmetric, and transitive. We'll start with reflexive, so that a number is equivalent to itself. And when we apply this relation to both sides, we get this expression on both sides, showing that any integer is equivalent to itself. We next have to prove symmetry. Is the relation still true if we swap the numbers around the equivalence sign? Applying the definition of this relation in both cases, shows that it is symmetric. The next thing to show is that it is transitive. This takes a bit longer to show. Applying the definition to two of these expressions gives us these two equations. Adding them together gives us this equation. We'll manipulate it to be this. Now we can subtract this term from both sides. And then we can pack this expression up into ordered pair notation to prove transitivity correct. So this is an equivalence relation. Now we'll have to show that the addition and multiplication that we've defined for integers are well defined. We'll start with addition. We'll let these two pairs of integers be equivalent to each other. Then the equivalence relation definition will cause these equations to be true. We can then manipulate them so that one of the variables will be the subject. We can substitute these expressions into another equation that will be derived. So we need to show that this equation is true to show that addition is well defined. We'll add these two numbers using the addition rule. We can then make these substitutions using the equations that we've derived earlier. We can then rearrange these numbers to give us this equation. Then we can subtract this term from both entries in the ordered pair, and the result will be equivalent. We can then add this to both entries in the ordered pair to get this integer, which is equivalent. We can then use the addition rule in reverse to get this equation, which is the addition of these two integers. So we've proven that addition is well defined. Now to show that multiplication is well defined for integers. We have to prove this statement so that the product is equal if the inputs are equal. So then we'll expand the right-hand side out using the product rule. Then we'll substitute these numbers into this expression to get this very messy expression. And then we'll manipulate it to get it ready for the next step. I've ran out of room, so I'll rewrite the last line here. I'll subtract this number from both sides to get this expression, which is equivalent. Then I'll add this number to both sides to get this number, which simplifies to be this. And then I can use the product rule in reverse to get this expression, so that now multiplication has been proven well defined for integers. So now we have to prove that the set of integers form a ring, that is, a set of numbers with certain properties, so that a lot of intensive math can be done with them. We have to prove these painfully obvious bracket swapping axioms and existence of numbers like 0 and 1. So now to prove that 0 is contained in this set, we'll define it to be this, with both numbers in the ordered pair being equal, so that their difference is 0. Now to prove that it is a 0, by watching whether it behaves like a 0, we'll add this 0 to an arbitrary integer in the set. We'll expand it out to be in ordered pair form. We'll use the addition rule in the forward direction, and this will be equivalent to the number that we were adding to 0 in the first place, so a 0 exists. So now to prove the existence of 1, which we'll set to be equal to this. The first number will always be 1 larger than the second. We'll multiply an arbitrary number by it. I've reused the symbol I to stand for the number 1 in integers. It usually stands for the square root of -1 in complex numbers. We'll expand it out to be 1 as we defined it for integers. We'll expand this expression using the product rule. We'll manipulate it to be this, so that a certain number can be subtracted from both members of this ordered pair. So now if we subtract this number from both members, we'll get this number, which is the number we started with. So the number 1 exists in the integers. Now to prove closure, we have to show that this number is in the set. And using the addition rule, we find that both members of the ordered pair are natural numbers. so that closure is satisfied for addition. Now we have to prove closure for multiplication, and we can see that after using the multiplication rule, this number is in the set as well, so we have closure for both operations. Now to show associativity, we'll have to move the brackets over to the last two integers to show that the order in which the addition is done doesn't affect the result. We'll expand it out using the addition rule. We'll apply the addition rule again and manipulate this expression a bit. We'll contract this expression by using the addition rule in reverse. And then we'll use the addition rule in reverse again, thus proving the result. We've successfully moved the brackets over to the last two integers. Now to prove associativity true for multiplication, we'll use a similar method as that used for addition. We'll expand it out using the multiplication rule. We'll use the multiplication rule again, thus getting this messy expression. We'll manipulate this expression to get it ready to use the multiplication rule in reverse on it. Using the multiplication rule in reverse, we'll separate the first integer out the front and contract this expression. We'll use the multiplication rule in reverse a second time, thus obtaining this expression, which is the first expression with the bracket flipped over to the last two integers. So we've successfully proven this axiom for both addition and multiplication. Now to show that distributivity is true, we have to manipulate the brackets in a different way. We'll use the addition rule to expand out this expression. We'll use the multiplication rule to expand it out again. We'll manipulate this expression so as to get it ready to contract it. We'll contract this expression using the addition rule in reverse. We'll contract it again using the multiplication rule on two separate expressions, thus getting the equation into this form, thus completing the proof. Now to show that addition is commutative, that is, that the integers can be swapped around the plus sign without changing the answer. We'll expand this equation using the addition rule. Then we'll rearrange this equation, and using the addition rule in reverse gives us this equation, which proves that addition is commutative. Now to show that every integer has a negative or opposite, and this is what it is. We have to show that it behaves like an opposite. We'll add this opposite to its corresponding integer. We'll expand this integer according to its definition. We'll add them up using the addition rule, and so it is equivalent to this integer, which is the definition of 0. So every integer has an opposite, which, when added to it, evaluates to the 0 integer. We've now proven that the set of integers is a ring, because we've proven all of the ring axioms. Now we can prove that the set of integers is an ordered ring, just by proving these two axioms. One involves addition, and the other involves multiplication. We'll define the less than operator to be a relation, so that this equation is true. And this is why it is true, because the differences for each of the integers obeys this equation. We'll now prove the addition axiom. We can expand this out using the definition of less than. We'll add this number to both sides to get this equation. We can manipulate this expression and use the definition for less than in reverse to get this expression. Then we can use the addition rule in reverse to get this expression. So we've proven the first axiom. Now to prove the multiplication axiom correct, we'll set these integers to be greater than 0 using the 0 integer in this form. We can get these two inequalities from these integer inequalities. We can manipulate one of these inequalities to be this. So this number is a positive or 0 number, and so it is a natural number. We'll multiply one of the equations by this number to get this equation. and the greater than sign isn't flipped because this number is positive or 0. We'll expand the brackets. We'll manipulate it using some algebra. We'll use the product rule in reverse to get this equation, which proves this axiom correct. So the set of integers is an ordered ring. We can lay all of these numbers on a line. So now to look at what integers actually are. In this picture, they are all of the possible jumps forwards and backwards. Backward jumps are negative integers. The set of all jumps 7 places forward is the integer 7. Looking at an integer in the xy plane, where x represents the first number and y the second, an integer is all of the ordered pairs that have the same value of x minus y. They are long diagonal strips of numbers at 45 degrees that continue forever, and terminate at the x and y axis, because this graph displays the natural numbers that don't include any negative numbers. Fortunately, these numbers don't have to be stored in a computer as an infinite set, but can be stored a lot more compactly. So I hope that you have enjoyed this video and felt that you have learned something from it. Please click like and subscribe if you have. Please leave some constructive criticisms and new ideas in the comments. Feel free to share these videos however you want. And thank you so much for watching.